I'm going to do an example of the optimization for a hexagon. To start with, we're going to draw the shape, and then we're going to split the shape into n amount of triangles, so 6 triangles in this case. Then we're going to take one of the triangles, just to work with one of them, and redraw it like this. So then, we know this one's going to be 10 units. And then we've got to get into a form so it's all in terms of one variable so it can differentiate it. So we're going to call the bit that we cut away, we're going to call that x. It's going to be the same on both sides. Which means the middle section here is going to be 10 minus 2x. To work it out, we're going to have to work out the area of this triangle and times it by the height. So to work out the area of this triangle, we're going to use the base times the height divided by 2. So we know the base, well, it's going to be half the base times the height. We know the base is equal to a half 10 minus 2x, which we can just write as 5 minus x. Now to work out this height, what we're going to have to do is we know this angle here. So we know this angle is going to be 30, so that means this angle is going to be 60. So to work out this height, we can do tan 60 times by this 5 minus x. And to work out the area of this triangle, we're doing a half, so the area equals a half the base, which is 5 minus x, times by tan 60. And then because it's times by 5 minus x again, we can just call this a 5 minus x squared. Right, now we've got to work out the area of the hexagon, sorry. So to do that, we've worked out one of these triangles, so we can just times that by 12, because there's going to be 12 of them in here. So we can just say that the area of the inner hexagon is going to be 6. 5 minus x squared times tan 60. Right, so now we've just got to work out this height here. So we'll call this capital H. In doing that, we're going to do it the same way, because we know this angle here, is going to be 60 again. And obviously we know that we've called this length here x. So this big H is going to be x times by tan 60. Right, and then to work out the total volume of the shape, it's just going to be, just rub this out, it's going to be, so the volume is going to be the area of the inner hexagon times by the height, which we've drawn here. So we can rewrite that as the volume equals this one, so 5 minus x squared tan 60 times in that by x tan 60. So we can rewrite all this as the volume equals 6x times by 5 minus x squared times by tan 60 squared. Right, and obviously that's just the volume for it. And to work out where it's going to be a maximum, we're going to have to take the derivative of it. So dv over dx is just going to be 150 minus 120 plus 18 So that's a 120x squared, and that's all going to be times by tan 60 squared. Right, so to solve it when it is a maximum, we're going to have to set dv over dx equal to 0. So we're just setting this equal to 0, and then we could say 150 minus 120 x plus 18 x squared times by tan 60 squared equals 0. So first of all, we're just going to get rid of tan 60, divide through by that, leaves us with this. So 150 minus 120x plus 18x squared is equal to 0. Now you can factorise that, and try it yourself. You factorise it down to 3x minus 5 times by x minus 5 equals 0. So, I'm just going to run this off. We have that x is equal to 5 over 3, or x is equal to 5. Now, we know this is a volume formula, and so I'll just rewrite that one a bit. If we put x is 5 into here, then we're going to get 0 times by everything. So it's not that one. So we're not. That's obviously the minimum. So the maximum is going to be when we put x is 5 over 3 into it, and we get that v equals 6 times 5 over 3 times 5 minus 5 over 3 squared times tan 60 squared. And because I'm a genius, I can do that in my head, and I know that v is equal to 1000 over 3, which equals 3.3 recurring units squared.
Actually, it's units cubed.